we would probably like to know what is the total capacitance. Right. In theory, all of these capacitors will work as if there were only one big capacitor, right? First thing. So how do we find this relationship? Well, we know the potential difference from here to this side is going to be V, right? That's the amount of potential we have from one side to the other. And it just happens to be the same amount when they're in parallel. All of these will have the same potential difference. Which is going to be the total potential difference. Remember this is important. If you haven't done chapter 5, you don't need to, just remember this. Potentials across parallel capacitors are all the same. So let's put this in red. Potentials across parallel is two straight lines. Parallel, let's just write it down. Parallel capacitors are always the same, right? So what does this mean? Right, so it's going to be, well, first equation is going to be, well, the total voltage is equal to voltage 1, which is equal to voltage 2, which is equal to the voltage 3, right? Let's look at the total charge then. You're going to have an amount of charge stored here. You have an amount of charge stored here and an amount of charge stored here. There are three different capacitors. There are three amounts of charge you can store. So if you want to ideally make this or model this as if it were only one capacitor, well, the total charge has to equal the sum of the charges, right? And, well, what was the equation for charge and capacitance? Well, if it was capacitance is equal to the charge divided by the voltage, right? So this is going to equal to, well, whatever the total voltage is, divided by the voltage across 1, the voltage across 2, divided by the voltage across the third one. So, right? And finally, well, you divide up everything by the same thing, basically. All these voltages are the same, right? So this is perfectly legal in your equation because you divide both sides by the same thing. This doesn't change the equation. So you end up, well, this was capacitance, but it's total capacitance. So total capacitance, C total, is equal to, well, this is also capacitance 1 plus capacitance 2 plus capacitance 3. So the final equation isn't very groundbreaking, right? This is very easy to memorize. So what is important to memorize here? Well, the important thing to memorize is not that this is equation for capacitance. This is already in your physics booklet. What you have to memorize is that for parallel capacitors, the voltages are the same, right? Because this is what helps you solve the problems later on. Okay. Of course, one thing that you should notice is capacitors in parallel always have a higher total capacitance here, right? And it makes sense. If you add them, you can't get a lower capacitance, right? The total always has to be greater. This might seem like very easy and logical, right? But it really, you need to know this to answer the problems as well. In particular, multiple choice questions, because it allows you to know which ones are the wrong ones, right? Okay, next thing is, well, we have parallel, we also have series, right? And on the top, the parallel ones were, well, parallel to each other, right? In the same direction. In series is that they're one after another, like this. So these are capacitors in series. Okay, so what helps us solve the total capacitance here? We want to know the total capacitance of this circuit, right? In this case, the voltages are not going to be the same, right? We know the voltages add up to the same thing. So if you have a voltage difference here, V1, and a voltage difference here, which is V2, across this one, well, they're going to equal to the total voltage. Right? Think of these as steps, right? This is like the total voltage is total height. Every capacitor brings you down a little bit closer to the bottom, right? Of course, if you go up, you go down the same amount. So these two have to be equal. What else? Well, second thing we know is the charges. Well, what about the charges? Well, the charges here, Q1, and here the Q2 charge have to be the same. And let's think about why this is, right? So this is a positive side, this is negative side, right? So this would be a positive charge. Here there's a negative charge, and let's put this in different colors so we can see the difference here. Let's put the negatives in blue. Let's put the positives in red or green. Let's put green. We already used red for voltage. Right? Same thing will happen here. There's a positive, 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 positive. There is a negative, 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 negative. Okay. But the thing is, whatever charge you have on one side, you have to also have on the other side, basically. Right? You can't have more charge on one side, right? Why? Because if you have more charge on the other side is going to try to get the same charge as well. So both sides of a capacitor have the same charge. That's number one. Number two is the charge in this side of this capacitor, right, came from here. What does this mean? Well, before these were charged, right? Let's say before it was charged, it was neutral. And I'm going to get rid of the charge sign here. So you see neutral light. Forget about the rest of this. If you want to put a charge on one side, right? If you want to put a positive charge here, it means the same amount of negative charge left here and came here. Right? If you want to put an additional amount of charge, then the same amount of charge here left here and came to the other side. Right? Because it was neutral before. Whatever charge you need to be here will also be the charge in this other side. Right? And this means, well, basically, this capacitor has the same charge as this capacitor. They cannot be any different charge. And if that's the case, right? Well, this is like it was only one big capacitor that one side has this charge, the other side has this charge, right? So this is also equal to, well, the total charge. Right? We're trying to simplify this so that it looks like if it's only one capacitor. And this one capacitor is going to have a capacitance of total. It's going to have a potential difference of V, right? And it's going to have a charge of Q total. So what do we do? Well, again, what was the equation for capacitance? Capacitance was equal to the charge per voltage, right? So let's divide this by charge. And so happens that if you divide both sides by the charge, let's put the charge in blue. So it's going to be divided by Q total, divided by Q1, divided by Q2. Right? What do we get? Well, just remember the voltage is in the bottom, right? This here, the voltage is in the top. So what you have to do is you probably have to get the capacitance, but it's reciprocal of the capacitance. So it's going to be 1 over the total capacitance equals 1 over the capacitance 1 plus 1 over the capacitance 2. Right? So, one thing. Let's give these actual numbers, right? Let's say the capacitance C1 equals 2 and the capacitance C2 equals 2 as well. I'm not going to give you units yet. But if you input this here, it's going to be 1/2 plus 1/2 equals 1 over the total. Right? And this is just 1, right? So the total capacitance has to equal to 1. And notice what happens. Capacitors in series always have a lower total capacitance. The capacitance went down, right? You don't add them. Actually, if you put them in series, you get a worse capacitor, right? So you probably don't want to be using series capacitors, right? What's the point, right? It just makes it store less charge. So now we have two equations, one for parallel, one for series. We probably have to practice using these